Okay, so here's the equation that we're going to work with. Um, we're going to do exactly the same thing we did before. So every place there's a u, we're going to introduce u is equal to u bar plus u prime. So the time averaged u velocity and then the fluctuating component. So that's, several places inside of here. And every place there's a v, v is going to be v bar plus v prime. So that'll be here. So that's what this is, right? You can see this derivative with respect to time is du bar plus du prime. This is u bar plus u prime squared. U bar plus u prime times v bar plus v prime. And then finally the second derivative of u bar plus u prime. So that's the first step, same as before. Second step, let's integrate over an integration time that's long compared to the turbulence time scales. So that's what this is doing now. So we've integrated over that time. And then we just have to examine every one of these terms one by one. And again, we're going to find that most of them fall into one of two buckets. We're integrating time average terms, which means we can just pull them out and they stay the same. We're integrating fluctuating terms, which means that they're just going to be zero. But there's a couple that actually don't go away. So all I've done from here to here is just break this up into a whole bunch of separate integrals, right? So this is du bar d time. This is du prime d time. This I actually had to do the expansion. So this is u bar plus u prime squared. So this is the x derivative of u bar squared, and then I have a 2u bar times u prime. So the x derivative of 2u bar times u prime, and then finally the x derivative of u prime squared. And then here I have the y derivative of u bar times v bar, and then I'm going to have, I guess, a u bar times v prime, a u prime times v bar, and then finally a u prime times v prime. So that's what these terms are. On the other side, I have the gradient of the free stream pressure, and then finally this is two second derivatives. So the second derivative of u bar with respect to y, and the second derivative of u prime with respect to y. Okay, so let's go through these terms and see where we get to. So, like I said, many of these terms are going to fall into two kind of boring categories. So let's look at the first boring category, which is I'm integrating a time averaged term. So for example, here I'm integrating the time averaged of velocity squared. So if I do that, so that's what I've done here, I'm integrating a constant because u bar is not a function of time. So I can pull that constant out, which I've done here, and this integral of time with respect to time is just time. So I get this term, right, sort of unchanged. So when you integrate a constant with respect to time, you get that constant multiplied by time. So there's a bunch of those terms. If we go through that, I've tried to box all the terms that sort of fall into that bucket. Those terms I can pull out of the integration. They just kind of persist, right? So here this term just comes out, this term comes out, this term comes out, and then over here on this other side, these two terms come out. So we're left with some other terms that are still in play in terms of being integrated. So that sort of leads us to the second kind of boring bucket, which is I'm integrating a fluctuating term, and it fluctuates as much above zero as it does below zero, right? So let's look at a case of that. So here I'm integrating u bar times v prime, right? So I'm integrating a constant multiplied by something that is greater than zero exactly as much as it is less than zero. So when I do that integral, I'm going to get zero, right? And there's a bunch of those terms that kind of fall into that bucket. So here's one, here's one. Obviously here's one, so I'm crossing them out, I guess, down here. Here's one, here's one, here's one, here's one, and then on the other side here's one. you'll notice there are two terms that are related to fluctuating components, but don't necessarily integrate to zero. So one that obviously doesn't integrate to zero is u prime squared, right? We'll come back to that. And one that looks like it might integrate to zero, but it turns out doesn't, is this u prime times v prime. So we're going to keep those, but we're going to cross out every other term that integrates to zero. And that's what I've done here. So we've simplified it quite a bit. And we'll move on to the next slide. So here I just have those couple of terms left that don't integrate to zero necessarily. So one that obviously doesn't integrate to zero is when I'm integrating something related to u prime squared, right? And I hope that's pretty obvious. U prime may exist above and below zero by the same amount during any integration time. If I square that, though, it's always going to be above zero. So this is not going to integrate to zero. In fact, it's going to be some number bigger than zero, right? So that's why I have to keep this one, at least for now. This one is less obvious, right? If u prime and v prime were truly just random events, completely uncorrelated to one another, you know, when u happened to fluctuate up, v would have an equal chance of fluctuating up as it does down. If that were the case, then this group would integrate to zero, right? But that's not actually the case, right? So u prime and v prime actually are what are called correlated quantities, in the sense that a positive u prime is going to induce, on average, a negative v prime, right? So these two things are related to one another. One causes the other, right? And to see why this is true, consider this velocity distribution right here. So here we have, I've plotted the average x velocity as a function of position from the wall, right? So here's the no slip condition, and here I'm, you know, traveling up towards the free stream, but there's this gradient, right? And the point is that if I have a positive v prime, what that physically means is that I'm actually taking a hunk of fluid from closer to the wall and moving it up away from the wall. I'm moving it in the positive y direction. And if you think about that, what that means is I'm taking some low velocity, low u velocity fluid, and I'm injecting it into a bunch of fluid that has higher u velocity. And what that's going to cause is that fluid to slow down. So a positive v prime is going to tend to induce a fluctuation in u, right? So these fluctuations are not decoupled from one another. They tend to be correlated to each other. If you actually could take real-time statistics, if you could take real-time data where you were measuring v and u, you would see in that data that every time v tended to go up a little bit, u would tend to go down a little bit, right? So these fluctuations are correlated to each other. And as a result, this term right here actually tends to be negative, right? So it tends to be negative. It tends to be negative more than it is positive, and therefore it does not integrate to zero. So that is a term that we have to keep. We have to keep both of these two terms. And in fact, these are the terms that, because we have to keep them, they actually represent the impact of the turbulent fluctuations on the momentum equation, right? So let's go on. One more thing that we're going to do to simplify our life is basically remember that we're still in a boundary layer, right? So we're still in a boundary layer, and the whole idea behind our boundary layer simplifications were that in a boundary layer, the boundary layer tends to be very thin relative to the characteristic length of the object, and as a result, things tend to change relatively slowly in the x direction, but they tend to change relatively quickly in the y direction, right? Because the boundary layer is so thin, as you go from the surface to the edge of the boundary layer, that happens over a small spatial extent. So gradients in y are bigger than gradients in x, everything else being equal. So I have here left over these two terms, right? Both related to fluctuations. One is a gradient of these fluctuations in x. The other is a gradient of these fluctuations in y. So provided that the numerator of both of these things are about the same, I would expect the denominator of this to be much bigger than this. In other words, assuming that u prime squared tends to have about the same magnitude as u prime v prime, I would expect this term to be very small relative to this term, right? And it turns out that, in a boundary layer, we know that v tends to be much less than u. But in a turbulent boundary layer, actually, the fluctuations in v tend to be about the same as the fluctuations in u, right? So it's not like because v, the magnitude is small, the fluctuations in v are small. That's not necessarily true, right? The magnitude of the fluctuations in u and in v are about the same. And as a result, the thing that we're taking the gradient of in these two terms, it's about the same size. And as a result, then I can get rid of this term, right? I can get rid of this term here as being much smaller than this term. So I'm left with only one term that I have to think about in my Reynolds average momentum equation, right? And that's what I've done here. So if we stare at this for a second, I have all the terms that I had in my original momentum equation here, right? This is, now written in terms of u bars. But because I'm writing these things in terms of time average velocities, and I need to account for the additional transport of momentum that occurs due to these turbulent eddies, I have this additional term here that I can't get rid of. This is an important term. In fact, in many parts of the boundary layer, this is going to be a dominant term, right? So this is my additional term relating to the fluctuating nature of the turbulent flow. So the last thing I'm going to do before I call it quits for the X momentum equation is basically put it back in the form that it was when I started. So this is not the typical way that we look at the X momentum. We're not usually thinking of du squared dx and du times v dy. So all I'm going to do is unpack it, right? So this du squared dx is 2u du dx. This du times v dy is u dv dy plus v du dy. And of course, then I can collect one of these u du dx's and this u dv dy, and that's what I've done here. And if I pull out the u, I see that what I have here is my Reynolds average continuity equation, which has to equal 0. So I can get rid of this term here, and I'm back here basically where I started, right? I have on the left side the inertia of the average flow. I have whatever pressure gradient might be helping to push the flow along. I have the original viscous shear, right, related to molecular diffusion of momentum. But I have this additional term here, which is related to momentum transport due to turbulent eddies. So I've done what I wanted in the sense that I have an equation here that governs the time average velocities. But it comes with this complexity of having a term that I have to have a model for, right? I have to be able to model this term, or I can't solve this equation, right? So that gets me farther. Right here I have my original momentum equation. This is the Reynolds average momentum equation. Here I have my original x momentum equation, my Reynolds average x momentum equation. If we did exactly the same set of steps over here to my energy equation, I would end up over here with my Reynolds average energy equation. And you can see that I get over here a set of terms that look exactly like my original terms. I just put a little overbar in every one, and I do again have this additional term that didn't go away, right? That is an artifact of the energy transport due to turbulent eddies, right? This v prime t prime term doesn't go away, and it doesn't go away for the same reason that u prime v prime doesn't go away, and that is that a positive v prime is going to take either high or low temperature fluid, depending on the temperature gradient, and move it right into a region of either higher or lower temperature fluid. And what that does is cause a temperature fluctuation. So what you would see if you had a velocity probe and a temperature probe in a turbulent boundary layer is that every time you notice that there was a positive excursion of the v velocity, so the v velocity tended to go up, you would see a corresponding either up or down blip in the temperature, right? So these two things are going to be correlated to each other, and that correlation is related to the fact that, you've got this hunk of fluid that's being moved around up and down by these turbulent eddies, right? And of course, we can't get rid of those. Those are important. So these are our Reynolds averaged equations. Okay, so one last thing to do before we stop, and that is to actually, bring these bring this turbulent term into the gradient so that it looks like another stress. So here's where we stopped here with the x-momentum equation. We had all these terms and then this additional term that is characterizing turbulent mixing. You'll notice that the viscous term has a ddy term, and of course the turbulent term also has a ddy term. So all I'm going to do here is bring the ddy outside here. So I have ddy of mu times du dy, and this is clearly then the viscous stress, right? Mu times du bar dy is the viscous stress based on the average u velocity. And then here I'll bring the ddy out of this integral. And what that lets me do then is combine this and this, and that's what I've done here, right? So I have a viscous stress, and then adding to it, I have this turbulent mixing, right? So they kind of do the same thing in that they're both a transport of momentum. It's just that I'm typically only used to thinking about this one. This is molecular diffusion. It's characterized by a molecular viscosity, right? And then this is my new term. Sometimes this is called a Reynolds stress because it's related to the turbulence in the flow, right? But it sort of adds directly. Remember, u prime times v prime is negative, so it adds directly to this viscous stress. And this is the thing that in the next couple of videos we're going to have to come up with models for if we want to solve this equation, which we do under very simple circumstances, and come up with the law of the wall. If we want to put this equation into a CFD program, then we have to come up with more complicated models for this. But in the end, this is the term we have to model if we want to model a turbulent flow. And then we can do the same thing here for the energy equation. So you'll notice that, again, I have this conduction term, so transport of energy by molecular diffusion, and then I have this new term, which is transport of energy by turbulent eddies. They both have a ddy in them, so it becomes possible to sort of put them on equal footing, I guess. So here I've just sort of expanded alpha as k over rho c, and said that the second derivative is ddy of dt dy. Here I'm just bringing the ddy out of the integral, right? And then I put them all together, and I see pretty clearly here that I have conduction, and adding to that conduction is turbulent mixing, right? So again, something we're pretty familiar with, and then something that's brand new, right? This is a term that we're going to have to come up with a model for if I want to solve this equation.